pleasure to announce the talk of Lucy Wegglers. She's a professor at the University of Applied Sciences in Berlin and present us the high-order BEM code on top of NGSolve NG-BEM. It's yours.
Thank you very much. It's a pleasure to be here and present my work, or our work, definitely our work on NG-BEM. It's a package, it's an add-on, and I want to tell you more about it. This morning we heard a lot of finite element methods. It's only finite element methods today, and now we have the little brother of the finite element methods. It's the boundary element methods, and I'm not sure how many people have used this method so far, so I want to go really quickly on the steps that you use, that you need to use for a boundary element method. So what is the standard boundary element method problem? So it's not that we can solve everything as with the finite element method. It's a couple of equations that we look at. It's the Laplace equation, Helmholtz, Maxwell's, Lamé equation, Stokes equations. Those are the boundary, the partial differential equations that we look at with boundary conditions. And the boundary element method, how to derive it. It's so that for these standard problems, we know how, in case it's a homogeneous problem, we know how the solution looks like, or we know an ansatz for the solution. And this ansatz for the solution is like a sum of layer potentials. It's a sum of layer potentials. We will in a minute see how this looks like, but for now, step one, you choose an ansatz for the solution. Second step, you derive from this ansatz a boundary integral equation for a density which is inside that ansatz. So in the layer potential, there's an unknown. It's a density on the boundary, and in step two, you derive an equation to get this unknown density. And then step three, you solve it, actually, with a variational formulation. As we see it in a finite element setting, you have also a finite element space. It's a finite element space on the boundary. And you end up with a linear system of equations that you solve. And you solve it for this unknown density on the boundary. So once you have it, you can plug it into your ansatz, and you know the solution of the PDE. So that's the step 5. Why is BEM beneficial? Yeah, we like it because the problem dimension is reduced by 1. So let's say you have a problem posed in 3D. The numerical problem, so the discretization problem, is posed on the boundary of that domain, so it's a manifold of dimension 2. So from 3D problem, you come up with a 2D problem. Second benefit is exterior problems are not an issue, meaning that if you have a PDE that you want to solve in an exterior domain, as you reduce it to the boundary, you don't have an issue with the exterior problem, right? So, and the third point is, yeah, the solution is very accurate. So we solve for the density on the boundary, and the solution accuracy is 1 order higher, at least, if you plug it into your ansatz and then evaluate your solution wherever you want. Why is BEM not everybody's darling? Yeah, why is it not so known or popular? It's not general as the finite element method. So, for instance, you need like linear isotropic material. Non-linearities are not really solvable. If you have a right-hand side on your PDE, that would involve a Newton potential. And Newton potentials are integral operators in the domain again. So you don't like it, right? It's a Newton potential you don't want. So it's that if you want to avoid Newton potentials, you consider the homogeneous equation, right? So second point is a homogeneous equation. The third point, you have to pay for this reduction on the boundary. You pay it with more difficult integration. We will see it in a moment. So your integral operators, they come with singular integral kernel, and that means that your naive integration rules won't work. So you have to deal with singular integral kernels. And the fourth point is different from FEM. You don't have sparse matrices, but dense matrices. So dense matrices. So those 2 points are, from numerical point of view, well known. And of course, there are solutions to that. And I want to quickly say what we did to tackle those problems. There are standard integration rules how to deal with these singular integrals. So they are very well documented, and we implemented special integration rules to deal with this problem. And the dense matrices, also this is in the BEM community a known problem, of course, and the point is that you approximate the matrices by so-called hierarchical methods. So the method that we implemented is the so-called adaptive cross approximation. So those 2 problems must be solved in a numerical code, and we did by special integration rules and ACA approximation. Now, when I came to Vienna and met Joachim, and we decided to work together on BEM, we had a vision, and I want just to tell you our vision. We want to implement a kernel-driven generic implementation of layer potential operators. So a generic point of view that will access all the problems that you had on the first list, right? Helmholtz, Laplace, Maxwell, everything. We want to implement the best that we have available right now, so that we have fast and accurate matrices. We want a plugin to NGSolve so that we can offer FEM-BEM couplings to everybody. We want, as you know it from NGSolve, a user-friendly Python interface. We want all potential for standard problems, so we want to implement those generic potential operators such that you don't need to implement the standard problems for yourself, but we offer the standard problems already. And of course, we want very good, well-documented and tested code. So this is the vision. Where are we right now? This was in November 2023. Now it's June. And I myself have these semester, wie sagt man, Verantwortlichkeiten. So I wasn't working on the code since March. Where are we now? So we have the generic implementation that's there. We have a first run, we have a first implementation of fast and accurate assembly of matrices. So the ACA approximation is inside the code, and also, of course, the dealing with the singular integral operators. It's compatible with NGSolve. There is a user-friendly Python interface. We have potentials for all standard problems, but tested and well documented. Please wait another 2 or 3 months, maybe in October. Next visit. Okay, so this is still open, and of course it's work in progress. We are not yet where we want. Especially, my PhD was about Maxwell's equations, so that's my personal there's my personal expertise. So I would like to have electromagnetic scattering for open screens in dielectrics. That's not yet in the code. It's the pack that I want to present you. But the dielectrics, they are not yet there. The low frequency EM scattering, that's my PhD work. I want also to have this in the code. That's a hybrid version, because you need also to stabilize the Maxwell's equations with an extra equation for the electrostatic potential. Non-trivial FEM-BEM couplings with artificial transmission conditions. That's wonderful. We need more examples to present and to show that there is so much potential inside this plugin. So we can, of course, show more if we have more time. Demos for, this is again Maxwell's equations. Demos for Helmholtz-Stokes and elasticity, they are not yet there, so we want to have that too. Maybe an alternative to ACA approximation is multipole approximation. It's if you would talk with people who do BEM in a commercial software, it's the gold standard, so it would be nice to have also this. We want to have a maybe I need to talk to Joachim with this pointwise evaluation of the representation formula. Right now we have an evaluation of the representation formula in an L2 sense, but there is potential to make it more fast and maybe also very nice documentation and more testing. So that's what are the next steps. And now I want to show you how it works. Maybe one more comment on this repository that you can also download and use. This is what I wanted to show you in the next 15 minutes. It's short and sweet. So concentrate on me and my speech. There's not so much comments around. And if you want to learn more about the steps behind, here are the detailed demos. And in the repository, there are also more demos. Okay? Okay, maybe 1 more minute to put it into a FEM world. The FEM examples that we saw today, not every example actually fits here inside this sequence, but this is the world of the FEM. It's the energy spaces that you know, H1, HDiff, HCurl, L2, related by those differential operators that you know they are working inside the domain. And when you go on the boundary, what happens is that you need to understand what are the traces of those guys. So every function in H1 has a trace. And the boundary element community needs to answer the question, where lives this trace? What is this? And it's very well known. It's nothing that I found. But actually, the trace spaces, they are also related by a sequence. It's the natural trace space that we find is the one that you see here on the top. It's related with the surface divergence and the surface curl operator, scalar operator. So this is a scalar field. This is vector valued field. This is scalar. In H-1/2 curl live densities which are tangential continuous. So the tangential component across an edge is weakly continuous. So you have to understand how this works for curved surfaces. That's also this related to what you said today, what you were talking about. So everything that Michael was talking about comes here also because you need to understand those traces. Because the whole boundary element formulation works with those. And the other trace is the so-called dual trace. And it's important if you, once you do BEM, you play with those both sequences. Especially for Maxwell's equations, you have to play with those two guys. One H-1/2 diff and H-1/2 curl. they are like, those are the traces which normal component over the edge is weakly continuous, and those are the ones which have tangential component which is weakly continuous. All right, so okay, this is the whole world of BEM, FEM and BEM spaces. And so it is not, it's not surprising that once we work with FEM-BEM in NGSolve, you have access to all the FEM spaces and you access the trace spaces by taking the trace, right? By taking the trace. And that's what we will see. They are natural trace spaces, and the natural ones, they are the ones here. You just get them, the incarnations in FEM code, the finite element spaces, just by instantiate the FEM space and then going on the boundary. And then we have the dual space, and in NGSolve, Joachim already implemented them as extra spaces. So you have here an extra space, the L2 space is an extra space, L2 surface it's called in NGSolve. And this guy is also, this is the edge diff surface. Those are implemented in NGSolve. Okay, so now let's look at the first examples. Demo 1, Laplace equation. We have the normal stuff. You implement, you load the packages, and then we want to solve the Laplacian for an bounded domain omega. So it's an interior boundary value problem with given Dirichlet data. And Dirichlet data, this is the trace operator. It means just you take the you take the u and you just get the values on the boundary. Okay, it's not a big deal. Now, okay, maybe I should. Once you go in that repository, you will see that I have this slide here and this slide here, boundary integral equations for Laplace, boundary integral equations for Maxwell, and we have to quickly just jump into this again to see the potentials. When I started this talk, I said that we have an ansatz for the solution of the boundary value problem. And now I call the ansatz functions potentials, layer potentials. And here they are. Those are the famous layer potentials. It's the single layer potential and the double layer potential. Those are, let's look at it, functions from x, right? Because this is an integration over y, so y will vanish and it stays x. X is the variable of that function. And here you see the kernel of the Laplacian, 1 over norm x minus y, and that's completely fine because x lives in the domain and not on the boundary, right? It's a smooth function, and it's sorry. Yeah, it's a 3D. Yeah, and this function is homogeneous. It's homogeneous. So it solves Laplace as L equals 0. And this as well. Both functions are homogeneous functions for any choice of M and J. But J must be at least h minus 1/2, and M should be h 1/2 on the boundary. Okay? So trace spaces. All right, but you keep in mind, this guy here, I call it SL, is a single layer potential, is a homogeneous function. So I can go in the demo for Laplace 1, and I say, okay, I want to solve Laplacian in the domain. Yeah, make an ansatz. An ansatz as single layer potential with unknown J. And with this unknown J, I have a freedom to find J such that the boundary condition is met. That's the boundary element idea, so Ansatz. And now the only thing that I need to solve for in order to solve this boundary value problem is to find J. So let's find an equation for this J, and the equation to this J is found in by applying a trace operator on that Ansatz. That's why you see here the trace operator. I applied the trace operator, so all those densities that come out then are like not real functions but distributions, so you should understand them in a weak form. That's the weak form. It's a variational formulation in the end of the day. And if you discretize them, this variational formulation, you end up with a matrix. It's called the single layer potential operator. J is your ansatz for your density, which is unknown. M is a mass matrix, and U0 is the Dirichlet data. And what is important for me to tell you today, and maybe like on Wednesday, is here you see the access that we choose in NG-BEM to offer you operators that implement exactly those matrices. This is the matrix V will be the single layer potential operator. And now the only question that you have to answer is, okay, what is the trial and what is the test function? What is the trial function and what is the test function? That's why you have here this overview. Okay, for the single layer potential operator, the trial function is h minus 1/2. This is the density, lives in h minus 1/2. The conforming finite element space is Laplace, is surface Laplace. And the FE test space is also surface Laplace. And this is what I already prepared in my in the before. You also have potential operators. They are in the BEM community called double layer potential operator. Is the guy that you get when you take the double layer potential as an ansatz function for the solution. And here you have another trial and the same test function. And the NGSolve trial space is just the natural space from the 3D NGSolve H1 space. Okay? So that's why when you get on this repository, you will find this structure, and here are the NG-BEM operators that you have to implement, and that's what we will see now. Here's a mesh. It's a sphere, right? We solve for omega is a sphere. Here you initiate the trial and test functions. Surface L2, the right-hand side as a linear form, as you know it. You are the experts for NGSolve. Here is the new operator, the single layer operator with trial and test function fs L2. It's what I initiated here is the int order, and here you say you want ACA approximation. Yeah, and now you have your system matrix to solve the linear system of equations with the C is an iterative solver. You must use an iterative solver because you have an approximation of the solution of the matrix as a linear system. And yeah, and here's the solution. It's not so very interesting. So let's look at other examples. The second example, it's a Neumann problem. I skipped the Neumann problem. I want to show you the third example. It's again Laplace with a capacitor problem. So you have like a plane to a capacitor. So you have Dirichlet conditions on those two blocks, and those Dirichlet conditions are the potentials fixed to a constant on top and on the bottom. And now we solve this with an double layer, what ansatz did I choose? I choose a single layer potential ansatz. And I choose what we call a direct method. So it's an ansatz that has a part, the single layer potential plus a double layer potential. Single layer plus double layer potential is a homogeneous function. And you get now why I choose this example is to show you that dependent on your ansatz, you get all different matrices. This is the single layer potential. This is the double layer potential. This is a mass matrix. And so you can just go through those demos and just find the NG-BEM routine to assemble those matrices. And that's what we find here. All those matrices are assembled, single layer, double layer, and mass matrix. And then we solve it again, and we find the numerical solution of this capacitor problem. So what you see here is now the trace, the unknown trace on the boundary, the Neumann trace on the boundary. And what you see next is, for the FEM community, it's not the trace which is interesting, right? We want to solve the partial differential equation inside the domain. So the post-processing is interesting, and the post-processing is evaluation of your ansatz. Now I don't know so I can zoom. Everybody sees it? I'm not with it. Like, yeah, you see it? So this is now, if you have the capacitor and you take a plane and you evaluate your solution on that plane, you get what we know is the electrostatic potential that we know from a capacitor. So now, quickly, I have 1 minute left. The Maxwell's equations. If you go to my repository, you will find exactly the same kind of presentation. We have our whole world of trace operators. We have 2 different potentials, and everything that comes turns around those 2 potentials. They are slightly more difficult because you have complex valued kernels. This is the single layer potential for Maxwell, and this is the double layer potential for Maxwell. And again, you have different types of operators that you get when you apply traces on those operators. And the classical problem that we study is the Peck scattering problem, meaning that you have a bounded domain with a perfectly conducting boundary, and you look for the scattered electromagnetic field. So this is the scatterer, and you solve an exterior problem, and this is the PDE that you solve. This time with radiation conditions, otherwise it's not well posed. This is an indirect formulation, so I make an ansatz as single layer potential. I derive my system matrix. It has in the BEM community exactly the same symbol, right? V is in the BEM community always the operator that is deduced by the single layer potential. It's not specified by, is it Maxwell or is it Laplace? It's always the V. Yeah? And you look into your problem that you want to solve. Now we have exactly the same notation chosen for the boundary, for the potential operators on the boundary, just that you have here the Maxwell in front. So, and here you have the trace spaces that you have to discretize that come with those potential operators. And now we look at that solution, that meaning screen, it is a scattering of a sphere, and why I was looking, what I wanted to show here is this is the numerical solution of the scattering problem in the BEM, meaning that you solve for the surface current that is induced by an incoming electromagnetic signal. And this problem has a unique solution, an analytic solution. That means that for this whole problem, I can do error analysis. It's the so-called me-scattering. And if you go and evaluate the solution, you get what the electrotechnic people know very well. It's the so-called this is the me-scattering far field. It's the me-scattering far field. And it's very, very nice. NGSolve, all what NGSolve can do in visualization is inside here. We just use the whole power of NGSolve to also like get a feeling for those solutions, right? And now comes the ship as the very last problem. This is what I, for the first time, was solving in 2011, and maybe a short story for mine. So when I was doing my PhD and implementing in Fortran this whole stuff, I was looking for non-trivial solution. A non-trivial solution meaning that you don't have an analytic solution. You just have the numerical stuff. And I was talking to an industry partner, and he gave me this ship geometry that you will see here. And I said I can solve the ship with high order Ansatzfunctions, high order. Because the numerical software just knows the linear edge elements, the linear elements. So, and then we did that comparison. I solved with order P for, like, you have to understand, it's order P, but you have like vector valued unknowns. It's not scalar. It's really vector valued scalar, vector valued problems. So, and I remember that day when I solved this problem. Here you have the ship, and you have the trace of the incoming plane wave that induces that scattered field, right? So this is a high frequency problem, and you cannot resolve that other than with higher order Ansatzfunctions, right? And I remember that day when I was working with my Fortran code and evaluated that problem, and then I did a polar plot, and I was just hoping that it's the same as what that enterprise gave me as like far field approximation, and it did, and it did very well. I did very well. So it's in my dissertation work where you see that polar plot, and numerical efficient is it because I just needed a third of the unknowns that they needed to solve that problem with the linear elements. So this is now the numerical solution of the Neumann trace. So this induces, I don't know how to work with this Mac.
Just 2 fingers.
To turn it? To turn it. So now you see that induced Neumann trace on that chip, and what you now have to do as a post-processing, you take that trace, put it into your representation formula, and get the solution everywhere you want. All right, so that's it. Thank you.
I think there is no need to be afraid of boundary elements. Right?
Yeah.
That's sweet, so questions to it. Lothar. Yeah.
Just one question. Is it a matrix-free algorithm? Because there you assemble and build the direct inverse?
It's not.
Is it need to do assembling, or is it?
Yeah. It's just hidden.
But compressed matrices.
Yeah, it's hidden here. It's hidden inside that this function. ACA, yeah.
Okay.
Here inside you have the ACA, and I didn't have enough time. If you go through that demos, you will see here. I tried to. This would be like a next step when I have some more minutes. Here you have optional arguments that specify the ICA approximation, right? So if you leave this aside, it would just take default variables, defaults.
So you have an H representation of your matrix. You recoded in NGSolve all the linear matrices and the H to represent the H.
Yeah, so they had it available from Saarbrücken, down there Tablet had it already, and we used it.
How does this compare with the other H2 compression library like HiKMA or?
I don't know.
Because you use PlatC, you can actually use
Yeah.
PyCMap.
Okay,
Yeah,
so
tomorrow,
that would be,
tomorrow,
would be a
tomorrow.
wonderful thing to work on further on that and to have more alternatives. Right now we have the ACA inside and nothing else.
Okay. Lucy is also here for the days and perfect initiation of the next PlatC. Thank you again,
All right.
Lucy,
Perfect.
and
Thank you.